wormhole simulation in quantum computer could bolster the theory that the universe is a hologram. Quantum experiment conducted on Google's Sycamore 2 computer transferred data across two simulated black holes, adding weight to the holographic principle of the universe. Physicists have used a quantum computer to simulate the first ever holographic wormhole and transported information through it. The baby wormhole created on Google's Sycamore 2 quantum computer was not created with gravity, but through quantum entanglement, the linking of two particles such that measuring one instantaneously affects the other. By entangling qubits or quantum bits in minuscule superconducting circuits, physicists were able to create a portal through which information was sent. The experiment has the potential to further the hypothesis that our universe is a hologram stitched together by quantum information. The researchers published their findings November 30th in the journal Nature magazine. This is a baby step for interrogating quantum gravity in the lab. Lead author Maria Spiropoulou, physicist at California Institute of Technology, said at a November 30th news conference. She said, "When we saw the data, I had a panic attack. We were jumping up and down, but I'm trying to keep it grounded," she said. Wormholes are hypothetical tunnels through space-time connected by black holes at either end. In nature, the immense gravity of the two black holes is what helps create the conditions of a wormhole, but the wormholes simulated in the experiment is a little different. It's a toy model that relies on the process called quantum teleportation to imitate two black holes and send the information through the portal. These processes appear to be pretty distinct, but according to the researchers, they may not be that different after all. An hypothesis called the holographic principle, the theory of gravity that breaks down around black hole singularities, Einstein's general relativity, could actually emerge from the weird rules governing very small objects like qubits, the quantum mechanics, and their experiment might provide the first clues that this is the case. Thankfully, the black hole analogous to the quantum computer are not the same as all-consuming monsters lurking in space, but the researchers are unsure whether they might have simulated the black holes closely enough for them to be considered strange variants of the real thing, ultimately dubbing their quantum computer rifts emerging black holes. It looks like a duck, it walks like a duck, and it quacks like a duck. That's what we can say at this point. Co-author Joseph Licken, physicist and the deputy director of research at Fermilab, said at the news conference, he said, "We have something that in terms of properties we look at, it looks like a wormhole." Einstein's predictions. The idea of wormholes first emerged from the work of Albert Einstein and his colleague Nathan Rosen, who in 1935 demonstrated in a famous paper that the theory of general relativity permitted black holes to be linked in bridges that could connect vast distances. The theory was an attempt to offer an alternative explanation to points in space called singularities, the cores of black holes where mass has become infinitely concentrated at a single point, creating a gravitational field so powerful that space-time is warped into infinity and Einstein equations collapse. If wormholes exist somehow, Einstein and Rosen reasoned, the general relativity held up. A month before the famous 1935 paper, Einstein, Rosen, and their colleague Boris Podolsky had written another. In that research, they made a prediction that, unlike their later paper in general relativity, was not intended to bolster quantum theory, but to discredit it for its ridiculous implications. If the rules of the quantum mechanics were true, the physicists outlined the properties of two particles could become inextricably linked, such that measuring one would instantaneously affect the other, even if the two were separated by an enormous gap. Einstein scoffed at the process, known as a quantum entanglement, dubbed it spooky action at a distance, but it has since been observed and is commonly used by physicists. Despite having produced these two groundbreaking predictions, Einstein's dislike for the inherent uncertainty and weirdness of quantum physics could have blinded him to a vital insight that the two predictions could be in fact connected. By separating general relativity and quantum theory, physicists have been left with no understanding of the realms where gravity and quantum effects collide, such as the interior of black holes or the infinitesimal point to which the universe was concentrated at the moment of the Big Bang. Holographic principle. Since Einstein reached this impasse, the search for where the big and small stitch together, the theory of everything, has led physicists to come up with all kinds of colorful propositions. One is the holographic principle, which posits that the entire universe is a 3D holographic projection of processes playing out on a remote 2D surface. This idea finds its roots in Stephen Hawking's work in the 1970s, which posed the apparent paradox that if black holes did indeed emit Hawking radiation from virtual particles randomly popping into existence near event horizons, they would eventually evaporate, breaking a major rule of quantum mechanics, that information cannot be destroyed. General relativity and quantum mechanics now no longer just seem irreconcilable, despite their many incredible accurate predictions. They could even be wrong. To solve this problem, proponents of string theory, who aim to reconcile quantum mechanics and relativity, used observations that the information contained by a black hole was linked with the 2D surface area of its event horizon, the point beyond which not even light can escape its gravitational pull. Even the information about the star that collapsed into the black hole was woven into fluctuations on this event horizon before being encoded onto Hawking radiation and sent away prior to the black hole's evaporation. In the 1990s, theoretical physicists Leonard Susskind and Gerard Hooft realized the idea need not stop there. If all the information of a 3D star could be represented in 2D event horizon, perhaps the universe, which has its own expanding horizon, was the same, a 3D projection of 2D information. From this perspective, the two disjointed theories of general relativity and quantum mechanics might not be separate at all. Space-time's gravitational warping, along with everything else we see, could instead emerge like a holographic projection, shimmering into a being from the minute interactions of tiny particles on the lower dimensional surface of the remote horizon. Testing for wormholes. To put these ideas to the test, the researchers turned to Google's Sycamore 2 computer, loading it with a bare bones model of a simple holographic universe that contained two quantum entangled black holes on either end. After encoding an input message into the first qubit, the researchers saw the message get scrambled into gibberish, a parallel to being swallowed by the first black hole, before popping out unscrambled and intact on the other end, as if it were spat out by the second. That's amazing. The physics that's gone on here, in principle, is if we had two quantum computers that were on different sides of the Earth, and if we improved this technology a little bit, you could do a very similar experiment where the quantum information disappeared in our laboratory at Harvard and appeared at the laboratory in Caltech, Lincoln said. That would be more impressive than what we actually did on a single chip. But really, the physics we're talking about here is the same in both cases. The surprising aspect of the wormhole trick is not that the message made it through in some form, but that it emerged completely intact and in the same order it went in. Key clues that the experiment was behaving like a physical wormhole, and that physical wormholes in turn could be powered by entanglement. The researchers noted that the information traversed a minuscule gap, just a few factors being that the shortest conceivable distance in nature, the Planck length. In the future, they want to design experiments of greater complexity, perform them on more advanced hardware, and send codes over greater distances. While going from sending information through their wormhole to sending something special, like a subatomic particle, does not take much of a theoretical leap. They say it would need a density of qubits greater enough to create a real mini black hole. Experimentally, I will tell you that this is very, very far away, Spiropoulou said. People come to me and ask me, can you put your dog in the wormhole? No, that's a huge leap, she said. This is by Live Science Ben Turner. Please leave your comments. Thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.